Okay, so welcome back to the lecture series of finite volume, and where we will continue our discussion where we left in the last lecture. So, if one look at a schematic, let us say we have this and we go top. So, this is the condition, this is the cell center value and this is the delta t. So, it is a boundary element. Here it is shows the boundary element and this is the cell center value, it moves towards that and this portion is delta t by 2 and this is where Ti is. Now, for the any other element, if you look at it, so what that happens, that they are at the now phase, this is the time step delta t and this is delta t by 2, this is also delta t and this is at Ti, and that is why for all the interior phases they are getting a gradient between phi at Ti plus 3 delta t by 2 between phi I t plus delta Ti plus delta t by 2. So, the difference between the two gradients is substantial, and any scheme that starts with this gradient will result in large initial error and that will affect the solution and the subsequent time steps. So, this error can be avoided if a grid similar to this one is adopted. In this case, the solution of the finite difference and finite volume methods will be basically similar as for a regular grid. So, one important thing is that one can understand that how important is the grid in numerical calculations, and then choosing proper spatial and temporal accurate scheme which will also have impact on the solutions. I mean, one can say or claim that he is getting a numerical solution done for a physical problem, but that may not make any sense. Now, once you adopt this approach, the upwind values at phases of the first temporal element, so that are obtained as rho c phi c Ti plus 3 delta t by 2 equals to rho c phi c Ti plus delta t and rho c phi c Ti plus delta t by 2 rho c phi c Ti. Now, substitute this one in the discretized equation, one get like Ti plus delta t minus Ti divided by delta t plus L phi c Ti plus delta t equals to 0. So, this is the similar one that you obtained for interior element. So, the boundary element thing can be modified so that you get the similar kind of expression for the interior element, and then now the important point is that so far whatever temporal discussion that we have been doing, we are in the framework of the uniform time step. It may not possible in a realistic situation that always you get an uniform time step. So, there could be possibility that you have non uniform time steps. So, if you get non uniform time steps, so it is very much common in practical applications, where the variable time steps are mainly used to reduce the computational cost by selecting a time at every time step and allowing the maximum allowable time step value, so that does not violate the CFL criteria. So, using the CFL criteria and every time iteration the allowable limit is decided, so that can effectively scale down the computational cost by certain factor. Now, for example, the first order scheme that we have discussed, the discretization typically not affected whether the time step is variable or constant. The situation is going to be different when we talk about second order transient scheme, since they use a tensile which involve two time step values. For the case of two step implementation like Crank-Nicolson has two steps implementation. So, where we use two step implementation like Crank-Nicolson type of scheme, nothing changes except that for each of the step a different time step is used. This affects the accuracy as a spatial derivative, as the spatial derivative is no longer at the center of the temporal element. For other second order scheme like second order upwind and this, the interpolation profile has to be modified to account for the non-equal time step. In what follows in the non-uniform transient grid is used in the discretization of the transient term of different schemes. Now, we can see like this non-uniform time step calculations in both the context of finite difference and finite volume. So, now we see the non-uniform time steps with FD approach. So, first we start with the Crank-Nicolson. So, the Crank-Nicolson, it is what it uses the rho phi at t plus delta t, which is rho phi t plus del t of rho phi at t delta t plus del 2 t by del t 2 rho phi at t square by factorial 2 and so on. Now, rho phi t minus delta t, which is rho phi t minus del phi by del t at t, it would be delta t naught, because here it is a non-uniform time step. So, the delta t is not equals to delta t naught. So, we make a difference and then we get to see what happens to the term. So, you multiply it with certain terms and then do some algebraic calculation, so that you can obtain the first derivative like del t of rho phi at time instant t, which can be approximated as delta t naught square rho phi t plus delta t minus delta t naught square minus delta t square into rho phi t minus delta t square and rho phi t minus delta t, which is divided by delta t naught square plus delta t naught delta t square, like that. Now, one can substitute the expression of this gradient in our discretization equation of the Crank-Nicolson. Now, one can get it for non-uniform time steps. So, once you substitute this, you get square rho phi, which uses at that time level t, minus del t naught, which is square minus delta t square, rho phi t minus delta t minus del t square rho phi t minus 2 delta t divided by delta t naught delta t plus delta t naught, where V c plus L phi c t minus delta t equals to. So, here you can see the discretized equation becomes like that. So, this would be, now this could be t minus delta t naught and t minus 2 delta t naught. So, and this would be t minus delta t naught, because we are saying that positive direction. So, t here when it goes this direction it is a delta t, when it goes this direction it is a delta t naught. So, this is current time level, previous, forward. So, the terms if you expand and the discretized equation, it will become A c dot plus A c into phi c t summation over f, which will use A f phi f t B c minus A c t minus delta t naught phi c t minus delta t naught A c t minus 2 delta t naught phi c t minus 2 delta t naught, where the coefficients are, this guy is essentially delta t naught divided by delta t plus delta t naught rho c V c, A c t minus delta t naught is delta t minus delta t naught divided by delta t plus delta t naught rho c t minus delta t naught V c, and A c t minus 2 delta t naught is delta t divided by delta t naught, delta t plus delta t naught rho c t minus 2 delta t naught V c. So, you can get the scheme which is recovered like that, and similarly you can do for SOUE, second order upwind Euler scheme, where you can use the phi values at t minus delta t, t minus delta t minus delta t naught, and so which uses t and other terms. Now, there if you put t minus delta t is rho phi t minus delta t by rho phi at t plus factorial 2 and delta 2 so on. Similarly, t minus del t minus del t naught, which can be computed as minus delta t plus delta t naught del t of rho phi at t delta t plus delta t naught square by factorial 2 del 2 phi by del t 2 at t and so on. Now, you multiply it with some factor and then do the algebra to get essentially the first derivative del rho phi by del t at t, which is nothing but 1 by del t 1 plus delta t divided by delta t plus delta t naught multiplied by rho phi t minus 1 plus delta t divided by delta t naught rho phi t minus delta t plus delta t square delta t into delta t plus delta t naught rho phi t minus delta t naught. So, if you put everything back in the semi discretized equation, this will look B c 1 by delta t plus 1 by delta t plus delta t naught and rho c V c minus B c 1 by delta t plus 1 by delta t naught rho c phi c t minus delta t plus B c del t by del t naught del t plus del t naught rho c phi c, which is t minus del t naught plus L phi c t 0. So, you can actually obtain back the discretized form. Now, sometimes one can use the now similar thing for the non uniform time steps with FVM, and what happens to that. Now, sometimes the delta t for this difference can be considered as del t is a arithmetic mean of this non uniform time step, that can be considered sometime. But now, similar thing if you expand for the finite volume and the thing which will start with the Crank-Nicolson. So, let us see what happens for the, this is the Crank-Nicolson for non uniform time steps. So, for non-uniform time steps, if you write the Crank-Nicolson, this is with FVM. Now, here you see these are the cell center and this is at the time level of t. So, t minus delta t by 2 is this, t minus, so this is delta t, this is delta t 0, this is delta t 00. So, this time is t minus delta t by 2, this guy is t minus delta t plus delta t naught by 2, and that is the way you get it, and this is a delta t, this is del t naught, del t double naught. Now, the term which is rho c phi c t minus del t by 2, now it will become del t naught by del t plus del t naught rho c phi c t plus del t by del t plus del t naught rho c phi c t minus del t naught plus del t by 2, and the other term which is rho c phi c t minus del t by 2 minus del t naught, which will be del t double naught divided by del t naught t double naught rho c phi c t minus del t naught plus del t divided by 2 plus del t naught divided by del t naught plus del t double naught rho c phi c t minus del t naught minus del t plus del t double naught by 2. So, once we discretize, put this in back in the discretized equation, the discretized equation will look like del t naught by del t plus del t naught V c by del t rho c phi c, which is essentially coming from this term t plus del t by del t plus del t naught minus del t double naught divided by del t naught plus del t double naught V c by del t rho c phi c. It is the term which comes from this. So, one can say that it is t minus this term. So, this can be, and the other term will del t naught by del t naught plus del t double naught V c by del t rho c phi c by double naught plus L phi c naught 0. Here this without script stands for the current time step, naught stands for the previous one which is this calculation, double naught stands for this. So, this is equivalent to double naught, this is equivalent to naught superscript, this is double naught. So, that is the way one can discretize the Crank-Nicolson scheme, and the fluxes can be written as flux C is del t naught by del t plus del t naught with rho V c by del t, flux C naught equals to del t plus del t plus del t naught minus del t double naught plus del t double naught rho c naught B c by del t, and flux V equals to minus t double naught divided by double naught plus rho c double naught V c phi c double naught by del t. So, similarly one can look at the second order upwind scheme. This is SOUE, where also you have this cell center value, this is T minus delta T, and this is T minus delta T, and if you put things back like rho phi at T plus delta T by 2, this would be rho phi T plus rho phi T minus rho phi T minus delta T plus delta T naught by 2 multiplied with delta T by plus delta T naught. Similarly, rho phi T minus delta T by 2 equals to rho phi T minus delta T plus delta T naught by 2 plus rho phi T minus delta T plus delta T naught by 2 minus rho phi T minus delta T naught delta T plus delta T double naught by 2, which is multiplied with delta T naught by delta T naught plus delta T double naught. So, if you put things back, it will semi discretized equation will look like del T plus del T naught V c by del T rho c phi c minus 1 plus del T by del T plus del T naught plus del T naught by del T naught plus del T double naught V c by delta T rho c phi c naught plus del T naught by del T naught plus del T double naught V c by del T rho c phi c double naught plus L phi c equals to 0, where flux C would be 1 by del T plus 1 by del T plus del T naught into rho c V c. Flux C naught would be minus 1 by del T plus 1 by del T plus del T naught plus del T naught by del T divided by del T naught del T double naught, which is rho c naught B c, and flux B is del T naught by del T by del T naught plus double naught rho c double naught V c phi c double naught. So, this is how you get all these term, and that is how you can get the unsteady discretizations for uniform and non-uniform grid. And so, we stop here today and look at the now flow field discretization in the next lecture.